We're going to look at the second example in OpenBDLM, where we're going to explore how can we have dependencies between several time series. So first step, we're going to start OpenBDLM, and then what we want to do is to create a new OpenBDLM file through the interactive tool. So we're going to type 0 to load the interactive tool. So what is the project name? Here we're going to call it example underscore distemp, because we have both displacement and a temperature time series, and we're going to have dependency between these two time series. Okay, I type return. So do I want to create synthetic data? No, this is not the goal here. What we're going to do is to create a database from scratch. So we're going to type the option 0. So here we're going to tell OpenBDLM where are our files. They're always contained in data, CSV. So this data is contained in example, this temp. So now I have two time series. So what I do is I'm going to select both time series and click on add. Both time series are here, done. So OpenBDLM is going to preload these time series. This is what we can see here. So the first time series is the displacement, this. The second one is temp for temperature. And what you can see is here, these little red dots represent the missing timestamps. So what we can see here is that the second time series represented temperature as some missing data. So what it means missing data, we have the timestamps there, but the values have nans, so mean the value is missing. So we can close this one. This represents the time step for each of my time series. So here the reference time step is 1 hour, but we can see that for many time steps, we can have gaps in the time series for each data set. So what OpenBDLM is going to do is to resynchronize automatically both time series so that they can have a common time steps. So we can close this one. And this is the raw data. What you can see here is the amplitude for the displacement, the amplitude for the temperature, and you can easily see that for the seasonal effects, we have a negative correlation, meaning that when the displacement is high, it's because the temperature is low, and vice versa. So we can close this one. So just like in example 1, one thing we want to do here is that the raw data has a time step of 1 hour. What we want to do is to resample this to decrease the time step to time step every 6 hours. So to do this, we're going to select option 4, resample. The new time step is going to be 0.25, so 0.25 day representing 6 hours. Okay, so now what we have is the data, and we can see that we have now new missing data in both time series caused by that resampling. And when I say resampling, what it means is I'm going to average all the data point I have over windows of 6 hours. This is what OpenBDLM does. I can close this one. And now I can choose option 7, save and continue. OpenBDLM is going to one last time print these time series. I can close them again. Okay, so now first step, I have my two time series. The first one is displacement, second one is temperature. So I need to identify the possible dependencies between these time series. So here, the question that is asked is, time series 1 depends on which time series? It actually depends here on time series 2. So displacement of a bridge is affected by, for instance, the temperature. So I am going to type 2. What is the dependence between time series 2 and other time series? The temperature is an independent quantity. So I'm going to type 0 to signal OpenBDLM. There's an absence of dependencies. How many model class we want? In this case, it's only one model class we want to use. So we have to define which component we want to use. So for my time series number 1, remember this is my displacement. So the only two components I want to use are going to be 11 and 41. 11 for a local level representing the baseline, and 41 for my residual term. It will capture my time-dependent model errors. Why don't I have any periodic components? Because these periodicity are going to come through the dependency over my temperature. We're going to see that next. So for now, for my first time series, only two components. First 11, local level, representing the baseline, and 41, my error term. For my temperature, in my time series number 2, now I want 11 for a baseline for the temperature. I want 2 periodic component, 31, 31. The first one, a period of 1 year. The second one, period of 7 days. And finally, 41 for my error term, I-type return. Everything has been configured. So here, first step, what we're going to do is to restrict our training period. So in this case, we're going to choose option 13 to restrict the training period. Option 1, first starting point in days for training period, 1, return. The n is going to be 180 days, we choose here. So 180, return, perfect. Now I'm at the point where I can learn my parameter values. So to do this, I can type 1. I can use the Newton-Raphson algorithm, option 1. Perfect, so training period is 180 days, maximum number of iteration. And here, what it does, that Newton-Raphson algorithm, is that modify all my parameter values that are described here. So we can see all the possible parameter values. And it wants to modify each of those to optimize each of those in order to maximize my log likelihood here. So keep in mind that this operation will take actually several minutes. So we're going to let it run. If in the meanwhile you want to skip this step, there's always a configuration file that is preloaded with the optimized parameter if you want to speed up the process. Okay, now all my parameters converge. It took roughly less than 5 to 10 minutes. So now what I can do is to estimate my initial hidden states. So for this, I can choose option number 2. It's going to compute my initial hidden state. That's going to greatly improve my time series decomposition. Compute the log likelihood. Perfect. Now I'm ready to choose option 3 to estimate my hidden states. So option 3, I can use either filtering or smoothing. So here I'm going to choose, for instance, smoothing, option 2. It's going to compute the hidden states. So computing the log likelihood, and it's going to return, it's going to plot all the time series or all hidden states. So here we have the autoregressive coefficient. So this represents again all the phenomena that I cannot explain with my component. So either through the local level or my periodic component or any of those things. So again, this is the residual term. The amplitude here is always to be interpreted correctly, because look at the amplitude here. You're going to see it's small in comparison with the overall amplitude of the time series. We can close this one. This represents my daily variability. We can close this one. And these are my hidden states for my temperature time series. This is for the daily variation. This is for my seasonal variation. So we can see that here, this is the amplitude of my seasonal variation that were separated from the raw data. And this is my local level for temperature. We can see that this is something that is constant here. Perfect. I can close this one. And this is the autoregressive term for my displacement. What you can see here is that the amplitude, again, is to be interpreted with care, because we always maximize the amplitude to be able to see what's going on correctly. So I can close this one. My local level, we see it's completely flat. And here, this is my temperature. So this is the temperature predicted by the model without any observation noise. And this is my predicted displacement. And here, the explanation of the predicted displacement here, the periodicity or the sign-like seasonal or daily effects are coming through dependency that comes from the hidden states. So in order to go look at those hidden states, what we can do is that we can export the configuration file. That's going to include the optimized parameters. So to do this, we're going to choose option 17. In order to export, we want to export the configuration file, option 1. So the function already exists. Do we want to overwrite? Yes. So we can go here in our folder. We can go in config file this time. We're going to have here, we have to quit. I'm going to have here my configuration file that I can use to reload the model. I have my model configuration directly here, my intercomponent dependencies. So basically, time series 1 depends on 2, time series 2 depends on no time series, and I have here all my parameter value. So what you can see here is all the parameters. What are those, the associated block name? What is the associated time series? So observation 1, then those are for observation 2. What are the bounds for optimizing each parameter? And what are their current value? And what we can see here as the last 3 parameters are the regression coefficient between here time series 1 and 2. So we have the 2 periodic component. The first periodic represents the yearly periodic component. The second one, the daily. We can see that here, for the yearly, we have a negative regression coefficient. For the daily, we have a positive one. So this is one of the things that OpenBDLM allowed to do, to have dependencies that can be of even opposite sign for long or short period. And this is something that's actually quite common for structural health monitoring, where we can have different external effects that have different interaction with the response of the system they are affecting. So we have all our config file if we want to reload it or restart from scratch. And if we go here in OpenBDLM, we're going to see that our new distant project is already loaded.